Hi, in this video we're going to have a look at this Mustool MDS8207. So this is a handheld multimeter with built-in oscilloscope functions with an analog bandwidth all the way up to 40 MHz. So let's take a little look at the listing on Banggood. So here we are on the Banggood website, and you can see it's currently retailing for about £80. If you are thinking about buying some electronics from Banggood, always have a look for discount codes because you can almost certainly get somewhere between 10 and 20% off the list price. But this is the Mustool MDS8207, 40 MHz bandwidth, 200 megasamples per second, and it also has a 6000 counts multimeter built in. If we have a look at the specifications, you can see we've got a 240 by 160 graphic LCD with 60 by 40 display area. And looking at the display, it's actually a really nice screen, so we've got a really decent resolution, which means that all of our fonts are rendered really nicely, and we've also got really good contrast with the negative display. I don't think the camera quite picks it up, but it's definitely a really nice feature about this multimeter. The multimeter specifications are nothing to shout about really, so the DC basic accuracy is 0.75% plus 10 digits. AC, which is always a little bit worse, is at 1% plus 10 digits, and you can see the rest of the specifications here are pretty much on a par with sort of a £30 to £40 low-cost multimeter that you'd expect to see. And the diode function has an open circuit voltage of about 3 volts. So one thing that's nice about Fluke multimeters in particular is they generally have quite a high open circuit voltage for diode tests, which means that you can really easily test your LEDs and that kind of thing. At 3 volts we can just about light up blue, green, white and UV LEDs with a test current of 2 milliamps. So if you're using it for anything other than testing signal diodes, you would be able to use it for seeing if LEDs are the right way around and that kind of thing. It has a 500 milliamp and a 10 amp fuse built into it, and we'll have a little look inside later. And then we've got the oscilloscope characteristics. So analog bandwidth is DC to 40 MHz with an 8-bit ADC, 1-bit non-linearity. I'm not sure if that's across the range. And then we've got our coupling mode DC and AC. The vertical sensitivity has settings from 500 millivolts per division all the way up to 200 volts per division. I'm not sure when you'd ever need to use that 200 volts per division. I'm certainly not thinking that I would be probing any high voltages with this meter, but it's certainly specified in order to be able to do that. In terms of the accessories in the box, you get a thermocouple for measuring temperature. You also get some test leads, and these do have PVC leads. The actual leads themselves are not that amazingly formed, so you can see there's some defects around here where the overmoulding is going over the red part of the probe, but these are pretty basic probes. So actually, these are slightly worse quality than the ones that came with the previous Mustool multimeter that I reviewed, but they're certainly fine for sort of benchtop use. They're just not the high quality probes that some may prefer. It also comes with this nice bag, and this actually does feel quite hard wearing, and certainly would protect your meter from scratches and that kind of thing if you were carrying this around in a little tool bag. So the PDVS2 Mini has been warming up for around an hour now, so it should be nicely settled. If you haven't watched my previous video on this device, this is a adjustable precision voltage reference produced by Ian Scott Johnston. So if you're not aware of his channel, I highly recommend that you take a look at it, and he's got lots of interesting projects on his channel, including some of the design and development of his PDVS2 precision voltage references. But what this means is that we can check how accurate this particular multimeter is. So this is technically a transfer standard, but I've tested it against my calibrated 6.5 digit multimeter, and it's accurate all the way down to the last digit pretty much. So for the purposes of this test, we can completely rely on the numbers being displayed on here as being the values that should be displayed on the multimeter. So we'll just put the probes in here. This is a little bit haphazard. Ideally we'd be using 4mm banana connectors, but this is fine for this test. And what we'll do is we'll increase the voltage to 1 volt. And you can see that took sort of 2 readings to get up to 1 volt. It's just reading very slightly under, but within spec. Let's increase it to 2 volts. And again, it's sort of 2 samples before it gets and settles to the final reading. This is on the 6 volt range, so let's take it past the 6 volt range onto the 7 volt range and see how long it takes to auto range. And there we go, it's still sort of the same amount of time. Let's see what happens if we try and get it to settle from 2 different ranges. So now it's at the 600 millivolt range. If we put the probes in, it needs to go to the 6 volt and then the 60 volt range. So let's try that. And yeah, that's pretty quick. That seems to be okay. And that's pretty much accurate up to 10 volts, so reading just very slightly under. Let's have a look at the resistance range. And I've got some precision resistors in this little box here, so we can see how accurate the meter is on resistance. And this is a 1K resistor reading just very slightly under 1K. And the 10K, again, just reading very slightly under. So that's pretty good, well within specifications. Let's have a look at the continuity beeper, because if you recall from my video on the old Mustool meter, the continuity test was extremely slow. So you can see on here that there's a few different ranges associated with this position. So we've got here ohms, diode test, continuity, and capacitance. So we can use the select button here to pick the continuity mode. So we'll go select. That's the diode test. And then we're on continuity. So let's try with the probes. So it's pretty good. It's obviously not as good as one of the much more expensive meters. It doesn't latch the continuity, but it is pretty quick. Certainly a lot better than the previous multimeter that we tested. Now let's have a look at the milliamp range. And this should be 50 milliamps or so. And just reading very slightly under. Let's take it up to 100 milliamps. So I'm reading 102 on the power supply, and it's pretty much 102 on the meter. This should be 401, and it's reading about 401. And this should be about 1 milliamp. And that's pretty much as close as we're going to get using the meter on the power supply. So that seems to be working okay. Let's just quickly check the 10 amp range. I don't expect this to be a problem. So that should be about 3.3 amps, so we're reading just very slightly under. So I think there's just generally a little bit of calibration error. It's just reading very slightly under on all of the readings. So we've now got the FY6900 signal generator, which I did a video on previously. As you know, I wasn't particularly happy with the power supply in this, so I am working on a new design using both a DC to DC converter stage and a linear power supply stage to give us an improvement in the efficiency, but also still give us the relatively low noise aspects. So what we're going to do is we're going to use this to test out the oscilloscope functions on the multimeter. So to use the oscilloscope, you put the leads in the OSC probe hole and then also in the common hole. And then we've got 2 settings here associated with the oscilloscope. So we've got the DC coupled and the AC coupled oscilloscope ranges. Let's set it to DC first. And if you have a look at the display, you can see now that we've got the oscilloscope display up on the multimeter. So we'll just set the leads into the adapter here and turn on the output. And you can see we're starting to get a signal on here. So to adjust the time base, you can see at the bottom here we've got a few little menu items associated with the function buttons underneath. So first of all we want to set the time base, so we press F1. And then you can adjust the time base with the left and right buttons. And there we go. So if you have a look at the bottom of the screen, you can see the voltage peak to peak. We've set this to 5 volts, so we're pretty much there. We've got the average of 0 volts because it's centered around 0 volts, so that's correct. And then we've got our RMS voltage, the root mean squared, which is 1.7 volts, so that's pretty much correct. And then you can also see we've got a little counter here, which is measuring the frequency, and we're outputting a 10 kilohertz sine wave, and indeed it is measuring that. So let's increase the frequency. And this should be 100 kilohertz, which you can see is being displayed here. Let's increase the frequency further. And now we're at 1 megahertz, and you can see it's not actually displaying a waveform because the ADC on this has started to alias, and now it's rejecting the signal. So we do need to adjust the time base further, and this is something that you need to be aware of, that if you aren't seeing anything on the screen, it's probably a good idea to use the auto setting function first, just to make sure that you aren't aliasing the signals. So we can either do this manually, and you can see if I just take it back a stage here, we're getting some weird signals as it's trying to sample that signal. So this is the problem with Nyquist and all that kind of stuff. The sampling is meaning that we're getting absolute garbage on the screen. Now we can quickly try out what the auto ranging is like, just so that we can see whether it can latch onto the signal properly. So we can press the R for the auto range, and you can see that very nicely gets back onto the signal. So that's a really quick way of setting up the oscilloscope without having to go through the faff of using the push button. So that works fine. Let's increase the frequency further. So now we're at 10 megahertz. It's still displaying 10 megahertz here on the counter section, and we're still getting 5 volts peak to peak. Let's adjust the time base a bit further. And increase the frequency even further. So we're looking good. That's 25 megahertz, 29, and then we're just starting to decrease in amplitude. And at around 35 megahertz, you can see we're at the minus 3 dB point. So the multimeter ADC is starting to roll off at this point. So we're not quite reaching the 40 megahertz bandwidth. And indeed, at 40 megahertz, the signal is almost gone on the oscilloscope. Now let's take a little look at the problem with using a multimeter like this for oscilloscope measurements. So we've got a square wave coming into the multimeter here, and it's working fine. So we're getting 100 kilohertz, and you can see the square wave here. If we increase the frequency some more, and we'll just auto set again. But if you look closely, what we're actually getting is quite a lot of ringing on this square wave, and that's the problem really with using these probes. There's no means of 50 ohm terminating at this end, so what we're getting is a mismatch in the impedances, and we're seeing the high frequency just reflecting up and down the probe cables, which is giving us this ringing signal. So you can see this is absolutely fine for just trying to see what's going on, but you just need to be aware that you're not going to be able to get a good idea of the signal integrity of anything other than a sine wave. So anything with high frequency content, you're going to get ringing because we don't have the appropriate probing setup. So we're now on the triangle wave, and this gives us an opportunity to look at the triggering options. And really, there's only two methods of triggering. If we go to the trigger menu, you can either trigger on the rising or the falling edge of the waveform. And if you have a look at the top here, we've got which side of the slope we're going to trigger on, and then the actual trigger voltage, which for some reason is set to minus 0.1 volts. But if we press the button here, we can switch between the rising edge, which it's currently triggering on now, and the falling edge, which you can see it's now triggering on the triangle wave. In terms of trigger modes, we've got automatic, we've got single trigger, and then we've also got normal mode. So the three modes that you'd typically expect. And then you can also set the trigger level. So we're currently at minus 0.1 volts. And you can see now we're triggering at 2.2 volts and we're almost at the peak of that triangle wave. So we've got some basic triggering functionality, nothing too exotic. This really is a multimeter designed for just looking at periodic waveforms rather than trying to decode serial waveforms or anything like that. Now what I've done here is just added some offset on the waveform generator so you can see we're no longer biased around the 0 volt point. And that means that we can now test out whether the AC functionality works properly, because what the AC function will do is put a capacitor in series with the signal so that we get rid of the DC offset and just look at the AC component. So we'll switch over to AC and you can see we've immediately dropped down and we're centered back around the 0 volt point. So that's pretty much all there is to the oscilloscope functionality of this multimeter. You can see it really is quite basic. It's just really designed to give an indication of what's going on in your circuit or in your device that you're trying to probe. So a little word about the look and feel of this meter. So considering that this is an £80 meter, the build quality is a little bit lackluster. So the whole thing is fairly plasticky and a little bit flimsy. It feels like it's made from ABS or something, but it's really not a high quality piece of equipment in terms of the look and feel. There's nothing really about it that oozes quality, and the banana jacks are also the basic banana jacks that you'll get on a very cheap multimeter. So the build quality sort of reflects what you'd get for £30 or £40. You're really paying the extra for the oscilloscope functionality. But the display is very nice and it does display quite a lot of nice information. The only thing really about the display is the whole thing is just a little bit slow. So you saw when I was reading the voltages, you just take that little bit of extra time to read the voltage. On the Fluke, it's probably twice as quick, maybe 3 times as quick to give you accurate readings, which is what you'd expect for something that's considerably more expensive. Right, so the battery compartment is actually part of the PCB, so the back cover actually has nothing in it other than the shielding, which is quite nice. It means that you don't have any flying wires going from the front to the back or anything like that. And we can see that it has just these very cheap split 4mm connectors, so nothing astounding about these whatsoever. If we have a little closer look in here, you can see we've just got very basic protection, and actually here are the fuses. So this is the 500 milliamp fuse, then we've got the 10 amp fuse. So if you are prone to blowing multimeter fuses, be prepared to do some desoldering and soldering to replace these, because these aren't really designed to be replaced by the looks of it. We've got some very basic protection. So this is the oscilloscope input, and we've just got this series protection here, and that goes off to the PCB. So that's just basically a thermistor. Similarly, on the voltage input here, we've also just got thermistor protection, and the fuses, obviously. We've got our series impedances to give us our 10 megohms, but there's really not much else going on. So you're probably quite unlikely to blow up the electronics in here. The 10 megohm impedances do tend to protect the electronics from that. But if you manage to create some kind of arc event inside here, there's not really much going on that's going to stop you just conducting a very high current through your probes and, you know, probably blowing up the probes and the multimeter as well. So I wouldn't really recommend this for use on high energy or high voltage voltage sources. It's probably best suited to benchtop use. Now if we have a look at the top here, we've actually got a PCB that's made from 2 stacks, and these are actually soldered together. I'm not going to take these apart because John Orbiter has already taken this multimeter apart. So if you haven't seen his video, I'll put a link to it above here, but I highly recommend that you take a look because he managed to get the PCB off and have a little closer look at what's going on under the cover. But basically we've got a microcontroller and an FPGA which is doing the signal acquisition, and that's about it really. So there's no dedicated multimeter chipset in here. They're doing it all with an FPGA and I think a microcontroller. We've got our crystal here, voltage regulator. We do have some capacitors flapping about here. It would have been nice to see these glued down, but it did survive the journey from China without any damage. But if you did drop this onto the floor, aside from probably cracking the plastic, you might see these and the inductor floating about inside the device as well. So there we go, that's a little look at the Mustool MDS8207. It's really not too bad, it's just a shame that it's priced just slightly high. Like I said, if you look for the discount code, you can probably get this more for around £60 or £70, which is starting to become a little bit more reasonable, because in terms of oscilloscope multimeters, this one probably has the nicest display, and I have used various oscilloscope multimeters, and the only ones that are worth using are considerably more expensive, so we're talking about £400 or £500. So in terms of sort of low-cost oscilloscope multimeters, this is probably the best out of the bunch. It's got the nicest display, and the user interface isn't actually that bad. So I've been using it quite regularly for about the past month or so, and not really had too many issues. I have used it for the oscilloscope functions as well as the multimeter, and yeah, I think really the main complaint is that on the multimeter ranges, just some of the readings can be a little bit slow to come up on the display. But other than that, it's really not too bad. Now, if you are thinking about buying an oscilloscope multimeter in place of a benchtop oscilloscope, I certainly wouldn't recommend it unless you spend, a significantly higher fee, because these are fine for periodic waveforms, but if you're trying to trace what's going on with some serial waveforms and that kind of thing, you're really just not going to capture it on here. It doesn't really give you the same ability to scroll around the waveform or anything like that. So this is really for periodic waveforms, just trying to see what's going on. If you want any precision measurements, you really need to go for a dedicated oscilloscope. So hopefully you found that video useful. I'll put a link down below in the description to the Banggood listing. But until next time, thanks for watching.